Hello and welcome to this lecture. In this lecture, we will discuss about networking in Kubernetes. Let us look at the very basics of networking in Kubernetes. We will start with a single node Kubernetes cluster. The node has an IP address, say it is 192.168.1.2 in this case. This is the IP address we use to access the Kubernetes node, SSH into it, etc. On a side note, remember if you're using a Minikube setup, then I'm talking about the IP address of the Minikube virtual machine inside your hypervisor. Your laptop may be having a different IP, like 192.168.1.10, so it's important to understand how your VMs are set up. So on the single node Kubernetes cluster, we have created a single pod. As you know, a pod hosts a container. Unlike in the Docker world, where an IP address is always assigned to a Docker container, in the Kubernetes world, the IP address is assigned to a pod. Each pod in the Kubernetes gets its own internal IP address. In this case, it's in the range 10.244 series, and the IP assigned to the pod is 10.244.0.2. So how is it getting this IP address? When Kubernetes is initially configured, we create an internal private network with the address 10.244.0.0, and all the pods are attached to it. When you deploy multiple pods, they all get a separate IP assigned from this network. The pods can communicate to each other through this IP, but accessing the other pods using this internal IP address may not be a good idea, as it's subject to change when pods are recreated. We will see better ways to establish communication between pods in a while. For now, it's important to understand how the internal networking works in Kubernetes. So it's all easy and simple to understand when it comes to networking on a single node, but how does it work when you have multiple nodes in your cluster? In this case, we have two nodes running Kubernetes, and they have IP addresses 192.168.1.2 and 1.3 assigned to them. Note that they are not part of the cluster yet. Each of them has a single pod deployed. As discussed in the previous slide, these pods are attached to an internal network, and they have their own IP addresses assigned. However, if you look at the internal network addresses, you can see that they are the same. The two networks have an address 10.244.0.0, and the pods deployed have the same address too. This is not going to work well when the nodes are part of the same cluster. The pods have the same IP addresses assigned to them, and that will lead to IP conflicts in the network. Now that's one problem. When a Kubernetes cluster is set up, Kubernetes does not automatically set up any kind of networking to handle these issues. As a matter of fact, Kubernetes expects us to set up networking to meet certain fundamental requirements. Some of these are that all the containers or pods in a Kubernetes cluster must be able to communicate with one another without having to configure NAT. All nodes must be able to communicate with containers, and all containers must be able to communicate with the nodes in the cluster. Kubernetes expects us to set up a networking solution that meets these criteria. Fortunately, we don't have to set it up all on our own, as there are multiple pre-built solutions available. Some of them are the Cisco ACI networks, Cilium, Big Cloud Fabric, Flannel, VMware NSXT, and Calico. Depending on the platform you're deploying your Kubernetes cluster on, you may use one of these solutions. For example, if you were setting up a Kubernetes cluster from scratch on your own systems, you may use any of the solutions like Calico or Flannel, etc. If you were deploying on a VMware environment, NSXT may be a good option. If you look at the Play with K8s labs, they use WeaveNet as their networking solution. So back to our cluster with the custom networking, either Flannel or Calico setup, it now manages the networks and IPs in my nodes and assigns a different network address for each network in the node. This creates a virtual network of all pods and nodes where they are all assigned a unique IP address. And by using simple routing techniques, the cluster networking enables communication between the different pods or nodes to meet the networking requirements of Kubernetes. Thus, all the pods now can communicate to each other using the assigned IP address. Hello and welcome to this lecture. In this lecture, we will discuss about Kubernetes services. Kubernetes services enable communication between various components within and outside of the application. Kubernetes services helps us connect applications together with other applications or users. For example, our application has groups of pods running various sections, such as a group for serving a front-end loads to users, another group for running back-end processes, and a third group connecting to an external data source. It is services that enable connectivity between these groups of pods. Services enable the front-end application to be made available to end users. It helps communication between back-end and front-end pods and helps in establishing connectivity to an external data source. Thus, services enable loose coupling between microservices in our application. Let's take a look at one use case of services. So far, we talked about how pods communicate with each other through internal networking. Let's look at some other aspects of networking in this lecture. Let's start with external communication. So we deployed our pod having a web application running on it. How do we, as an external user, access the web page? First of all, let's look at the existing setup. The Kubernetes node has an IP address, and that is 192.168.1.2. My laptop is on the same network as well, so it has an IP address 192.168.1.10. The internal pod network is in the range 10.244.0.0, and the pod has an IP 10.244.0.2. Clearly, I cannot ping or access the pod at address 10.244.0.2 as it's in a separate network. So what are the options to see the web page? First, if we were to SSH into the Kubernetes node at 192.168.1.2, from the node we would be able to access the pod's web page by doing a curl, or if the node has a GUI, we would fire up a browser and see the web page in a browser following the address http 10.244.0.2. But this is from inside the Kubernetes node, and that's not what I really want. I want to be able to access the web server from my own laptop without having to SSH into the node and simply by accessing the IP of the Kubernetes node. So we need something in the middle to help us map requests to the node from our laptop through the node to the pod running the web container. This is where the Kubernetes service comes into play. The Kubernetes service is an object just like pods, replica set, or deployments that we worked with before. One of its use case is to listen to a port on the node and forward requests on that port to a port on the pod running the web application. This type of service is known as a node port service because the service listens to a port on the node and forward requests to the pods. There are other kinds of services available which we will now discuss. The first one is what we discussed already, node port, where the service makes an internal pod accessible on a port on the node. The second is cluster IP, and in this case, the service creates a virtual IP inside the cluster to enable communication between different services, such as a set of front-end servers to a set of back-end servers. The third type is a load balancer, where it provisions a load balancer for our application in supported cloud providers. A good example of that would be to distribute load across the different web servers in your front-end tier. We will now look at each of these in a bit more detail along with some demos. In this lecture, we will discuss about the Node Port Kubernetes service. Getting back to Node Port, a few slides back, we discussed about external access to the application. We said that a service can help us by mapping a port on the node to a port on the pod. Let's take a closer look at the service. If you look at it, there are 3 ports involved. The port on the pod where the actual web server is running is 80, and it is referred to as the target port because that is where the service forwards the request to. The second port is the port on the service itself. It is simply referred to as the port. Remember, these terms are from the viewpoint of the service. The service is in fact like a virtual server inside the node. Inside the cluster, it has its own IP address, and that IP address is called the cluster IP of the service. And finally, we have the port on the node itself, which we use to access the web server externally, and that is known as the node port. As you can see, it is set to 30,008. That is because node ports can only be in a valid range, which by default is from 30,000 to 32,767. Let's now look at how to create the service. Just like how we created a deployment, replica set, or pod in the past, we will use a definition file to create a service. The high-level structure of the file remains the same. As before, we have the API version, kind, metadata, and spec sections. The API version is going to be v1. The kind is, of course, service. The metadata will have a name, and that will be the name of the service. It can have labels, but we don't need that for now. Next, we have spec, and as always, this is the most crucial part of the file, as this is where we will be defining the actual services, and this is the part of a definition file that differs between different objects. In the spec section of a service, we have type and ports. The type refers to the type of service we are creating. As discussed before, it could be cluster IP, node port, or load balancer. In this case, since we are creating a node port, we will set it as node port. The next part of a spec is ports. This is where we input information regarding what we discussed on the left side of the screen. The first type of port is the target port, which we will set to 80. The next one is simply port, which is the port on the service object, and we will set that to 80 as well. The third is node port, which we will set to 30,008 or any number in the valid range. Remember that out of these, the only mandatory field is port. If you don't provide a target port, it is assumed to be the same as port, and if you don't provide a node port, a free port in the valid range between 30,000 and 32,767 is automatically allocated. Also note that ports is an array, so note the dash under the ports section that indicate the first element in the array. You can have multiple such port mappings within a single service. So we have all the information in, but something is really missing. There is nothing here in the definition file that connects the service to the pod. We have simply specified the target port, but we didn't mention the target port on which pod. There could be hundreds of other pods with web services running on port 80. So how do we do that? As we did with the replica sets previously, and a technique that you will see very often in Kubernetes, we will use labels and selectors to link these together. We know that the pod was created with a label. We need to bring that label into the service definition file. So we have a new property in the specs section, and that is called selector, just like in a replica set and deployment definition files. Under the selector, provide a list of labels to identify the pod. For this, refer to the pod definition file used to create the pod. Pull the labels from the pod definition file and place it under the selector section. This links the service to the pod. Once done, create the service using the kubectl create command and input the service definition file, and there you have the service created. To see the created service, run the kubectl get services command that lists the service, the cluster IP, and the mapped ports. The type is node port as we created, and the port on the node is set to 30008 because that's the port that we specified in the definition file. We can now use this port to access the web service using curl or a web browser. So curl to 192.168.1.2, which is the IP of the node, and then I use the port 30008 to access the web server. So far we talked about a service mapped to a single pod, but that's not the case all the time. What do you do when you have multiple pods? In a production environment, you have multiple instances of your web application running for high availability and load balancing purposes. In this case, we have multiple similar pods running our web application. They all have the same labels with a key app and set to a value of my app. The same label is used as a selector during the creation of the service. So when the service is created, it looks for a matching pod with the label and finds 3 of them. The service then automatically selects all the 3 pods as endpoints to forward the external request coming from the user. You don't have to do any additional configuration to make this happen. And if you're wondering what algorithm it uses to balance the load across the 3 different pods, it uses a random algorithm. Thus, the service acts as a built-in load balancer to distribute load across different pods. And finally, let's look at what happens when the pods are distributed across multiple nodes. In this case, we have the web application on pods on separate nodes in the cluster. When we create a service, without us having to do any additional configuration, Kubernetes automatically creates a service that spans across all the nodes in the cluster and maps the target port to the same node port on all the nodes in the cluster. This way, you can access your application using the IP of any node in the cluster and using the same port number, which in this case is 30008. As you can see, using the IP of any of these nodes, and I'm trying to curl to the same port, and the same port is made available on all the nodes part of the cluster. To summarize, in any case, whether it be a single pod on a single node, multiple pods on a single node, or multiple pods on multiple nodes, the service is created exactly the same without you having to do any additional steps during the service creation. When pods are removed or added, the service is automatically updated, making it highly flexible and adaptive. Once created, you won't typically have to make any additional configuration changes. That's it for this lecture. Head over to the demo and I will see you in the next lecture. In this demo, we're going to take a look at services in Kubernetes. In the previous demo, we created a few pods by creating a deployment. So let's check the status of that first. So we have a deployment called myapp-deployment, and it has 6 replicas, which is essentially 6 pods running in the Kubernetes cluster. So now we have an application which is created to run on this cluster. But in order for the end user to access it on their web browser, we have to create a service. And to do this, let's jump back to our editor. We have created a new directory called service. And within this service directory, we're going to create a new file called service-definition.yaml. Note that you don't really need to follow this directory structure as I'm doing. I'm just following it to organize the examples. You could simply have all the files in the same location. And just like before, the first thing that goes in is the root element, the API version. And for service, it should be set to v1. For kind, we're going to specify service. So let's look that up from the list, and we're going to add metadata with the name of the service, which we can say my app-service. And underneath that, we're going to add the spec section. And the first property that we will create is the type of service, which we will set to node port. Now, our goal is to be able to access our application on a port on the node, which is the Minikube node in our case. And then we will add the port and the default port at which Nginx listens, which is 80. And we're also going to add our target port, which is also port 80. So this is basically the port on the service itself. And next, we're going to add a node port, which we can set to a value such as 30,004. So it could be any value between 30,000 and 32,767. And this node port is the port on the node, the worker node, which is the Minikube node, on which the application will be made accessible. Next, we're going to add a selector, which helps us bind our service to the port with the same label. So quickly, let's check the deployment YAML file, and you'll notice that the label for the pod is app set to my app. So let us add the same value here under the selector section. So once this has been completed, our service definition file is complete, and we can proceed to create this on our clusters. And I'm going to save it here and jump back to my terminal. And let me navigate to the new directory that we created. And here is our service definition file. So I'm going to create the service using the kubectl create command with the -f option and specify the service definition.yaml file as the input. Run this command and the service has been created. We can now run the kubectl get service command, and here you'll notice that the new service is visible, and the type of the service is node port, which because we want it to be accessible on the port on the worker node. And here is the cluster IP, which is also created for the service. Now, it's an address created for the service within the internal cluster network. And here is the port on the worker node that we can use to access our application. So if you know the IP of the worker node, you can simply go to a browser and just type in the IP of the worker node followed by the port number, and you should be able to access this application. Now, since we are running this on Minikube, we can also run the Minikube service command followed by the name of the service, which is the my app-service, and use the option --URL, and it should print us the URL with the service where the service is available. So let's try to access this on a browser. So you can just copy this URL, go to a browser, and paste that URL in the browser, and we see the default Nginx web page. So that confirms that the Nginx application is up and running, and we're able to access it on a web browser. Well, that's it for this demo, and I will see you in the next one. Hello and welcome to this lecture. In this lecture, we will discuss about the Kubernetes service cluster IP. A full stack web application typically has different kinds of pods hosting different parts of an application. You may have a number of pods running a front-end web server another set of pods running a backend server, a set of pods running a key value store like Redis, and another set of pods may be running a persistent database like MySQL. The web frontend server needs to communicate to the backend servers, and the backend servers need to communicate to the database as well as the Redis services, etc. So what is the right way to establish connectivity between these services or tiers of my application? The pods all have an IP address assigned to them, as we can see on the screen. But these IPs, as we know, are not static. These pods can go down anytime and new pods are created all the time, and so you cannot rely on these IP addresses for internal communication between the application. Also, what if the first front-end pod at 10.244.0.3 need to connect to a backend service? Which of the three would it go to, and who makes that decision? A Kubernetes service can help us group the pods together and provide a single interface to access the pods in a group. For example, a service created for the backend pods will help group all the backend pods together and provide a single interface for other pods to access this service. The requests are forwarded to one of the pods under the service randomly. Similarly, create additional services for Redis and allow the backend pods to access the Redis systems through the service. This enables us to easily and effectively deploy a microservices-based application on Kubernetes cluster. Each layer can now scale or move as required without impacting communication between the various services. Each service gets an IP and name assigned to it inside the cluster, and that is the name that should be used by other pods to access the service. This type of service is known as cluster IP. To create such a service, as always, use a definition file. In the service definition file, first use the default template, which has API version, kind, metadata, and spec. The API version is v1, kind is service, and we will give a name to our service. We will call it backend. Under specification, we have type and ports. The type is cluster IP. In fact, cluster IP is the default type, so even if you didn't specify it, it will automatically assume the type to be cluster IP. Under ports, we have a target port and port. The target port is the port where the backend is exposed, which in this case is 80, and the port is where the service is exposed, which is 80 as well. To link the service to a set of pods, we use selector. We will refer to the pod definition file and copy the labels from it and move it under selector. And that should be it. We can now create the service using the kubectl create command and then check its status using the kubectl get services command. The service can be accessed by other pods using the cluster IP or the service name. Let us now look at another type of service known as the load balancer type. So we have seen the node port service that helps us make an external facing application available on a port on the worker nodes. So let's turn our focus to the front-end applications, which are the voting app and the result app. Now we know that these pods are hosted on the worker nodes in a cluster. So let's say we have a 4-node cluster, and to make the applications accessible to external users, we create the services of type node port. Now, the services with type node port help in receiving traffic on the ports on the nodes and routing the traffic to the respective pods. But what URL would you give your end users to access the applications? You could access any of these two applications using IP of any of the nodes and the high port the service is exposed on. So that would be 4 IP and port combinations for the voting app and 4 IP and port combination for the result app. So note that even if your pods are only hosted on 2 of the nodes, they will still be accessible on the IPs of all the nodes in the cluster. say the pods for the voting app are only deployed on the nodes with IP 70 and 71, they would still be accessible on the ports of all the nodes in the cluster. So that's how a service is configured. So you would share these URLs to your users to access the application. But that's not what the end users want. They need a single URL like example votingapp.com or the example resultapp.com to access the application. So how do you achieve that? Now, one way to achieve this is to create a new VM for load balancer purpose and install and configure a suitable load balancer on it, like HA proxy or Nginx, etc. Then configure the load balancer to route traffic to the underlying nodes. Now, setting all of that external load balancing and then maintaining and managing that can be a tedious task. However, if we were on a supported cloud platform like Google Cloud or AWS or Azure, I could leverage the native load balancer of that cloud platform. Kubernetes has support for integrating with the native load balancers of certain cloud providers and configuring that for us. So all you need to do is set the service type for the front-end services to load balancer instead of node port. Now remember that this only works with supported cloud platforms. So GCP, AWS, and Azure are definitely supported. So if you set the type of service to load balancer in an unsupported environment like VirtualBox or any other environments, then it would have the same effect as setting it to node port, where the services are exposed on a high-end port on the nodes. It just won't do any kind of external load balancer configuration, right? So later on, when we walk through the demos of deploying our application on cloud platforms, we will see this in action, right? So that's it for now. I will see you in the next lecture.
Hey, in this video, we're going to walk over the solution for the lab on services. So the first question is, how many services exist on the system? So we're going to run the kubectl git service command, or you could also run the kubectl get svc command. It's a short for service. And we can see that there's just one service. So select that. So this is a default service created by Kubernetes. Okay. So what is the type of the default Kubernetes service? If you look at the type here, we see that it's cluster IP. So let's select cluster IP. We'll look at what this service is in particular later when we talk about the Kubernetes architecture, the API server in more detail. But for now, let's just consider it as any other service. So what is the target port configured on the Kubernetes service? So for this, you've got to look at the service in more detail. So we're going to do a kubectl describe command. And we're going to describe the service named Kubernetes. So here we see the port details. So the port is 443. The target port is 6443. So the question is, what is the target port? So we'll select 6443. Okay, how many labels are configured on the Kubernetes service? So if you look at this right here, so there are two labels. Component is API server and the provider is Kubernetes. So this service is basically the Kubernetes API server. We'll discuss more about the API server and this service specifically when we learn about the API server in detail and in the CK course when we get to that. So for now, the answer is 2. Okay, the next question is, how many endpoints are attached on the Kubernetes service? So for now, we have no idea what the service is. Since this service was already created, we don't really know what it is, so we're kind of exploring and finding out more about it. But one thing, if we want to look at right here and understand, is how many pods this is the service directing traffic to. So that's what you can see here in the endpoints section here. So endpoints, it says there's this one IP and port, so that's one endpoint. if there were multiple pods that the service is directing traffic to, then there would be multiple ports here. Let me quickly explain what endpoints are, because we have not really discussed about endpoints. Okay, so here we have a service and 3 pods. And what we do usually is when we create a pod, we know that it has a label to it. So let's say, for example, it's set to app and FE for front end or something. And the way that we create a service in order to direct traffic to these pods is we provide the same labels as selectors to the service. And then what the service does is it identifies all the pods with the same label and then directs traffic to those pods. So once it identifies the pods with the labels, that's when the service has these endpoints. So from the perspective of a service, endpoints are basically these, the pods. The pods that the service has identified that is going to direct traffic to based on the selector specified on the service and the labels on the pods. Now, when we create a service for a set of pods, now we might think that depending on the label and the selector we specified, the service is going to direct traffic to those pods. But it might be possible that we have another pod, which we accidentally created with the same kind of label. So the service is then going to direct traffic to that pod as well. So, and that's when we look at the output of the kubectl describe command, that we can identify the additional endpoints apart from what we thought we had configured. Right, so we're going to see, when you look at the kubectl describe command for the service, we're going to see that there are 4 endpoints. But in fact, our application had a replica set, perhaps that just had 3 endpoints or 3 pods. So that's where the endpoint can help. And just to give you a bit more context, so let's say we have a single pod and we create a service. We set a label to FE, but we accidentally set the selector to, say, FR, something that's different. And then when we try to access the service, we're not able to get through to the application. And that's when you look at the description of the service and you realize that the endpoints are 0. So that means the service has not identified any pods, right? So, and then that's when we can look at the labels and selectors in more detail to identify the root cause. So that's what endpoints are. It's nothing but it's a specification of all the pods that particular service has identified based on the selectors and the labels set on those pods. Okay, so in this case, this particular Kubernetes service has just one endpoint. So we're going to select 1 here. Okay, the next question is how many deployments exist on the system now in the current default namespace? So let's identify deploy. There's just 1 deployment, so we're going to select 1. Okay, so the next question is what is the image used to create the pods in the deployment? So we're going to look at the deployment in a bit more detail. And we see the image is codecloud/simple web app red. So that's this one. Okay, are you able to access the web app UI? Try accessing the web application UI using the tab at the top. So there's the link here, and clicking on it, we see that it gives us a bad gateway error. So the answer is no, we're not able to access the web app UI. So, and that's really because there's no service, right? So we have to create a new service to access the web application using the service definition.yaml file. So there is a service definition.yaml file here, and we look at it. So this is basically a kind of a file with the basic framework to create a service. So we'll use that and update the details that are given here. right? So we're going to set it, give it a name, set the node port and all the different ports, and also specify the selector. Now, if you're not sure about getting this framework, you could go to the Kubernetes documentation pages, search for service, and select service. And here you kind of get a sample that you can then copy and use. So we will talk about imperative ways or commands to create service in the upcoming lectures. For now, let's just go with this. So the name is web app service. Type is node port. Target port is 8080. And port is 8080. Node port is 30080. And the selector name is simple web app. Okay, let's create that service. Okay, that's done. Let's check. Okay, let's try to access this now. Okay, so that's working. So as I said, in the upcoming lectures, there is a section where we talk about imperative commands, and we'll discuss how we can create a service. So there are different ways of creating a service, and we'll discuss about that when we get there. For now, that's the end of this lab.
Hello and welcome to this lecture. In this lecture, we will try and understand microservices architecture using a simple web application. We will then try and deploy this web application on multiple different Kubernetes platforms, such as Google Cloud Platform.
I'm going to use a simple application developed by Docker to demonstrate the various features available in running an application stack on Docker. So let's first get familiarized with the application, because we will be working with the same application in different sections through the rest of this course. This is a sample voting application which provides an interface for a user to vote and another interface to show the results. The application consists of various components, such as the voting app, which is a web application developed in Python to provide the user with an interface to choose between two options, a cat and a dog. When you make a selection, the vote is stored in Redis. For those of you who are new to Redis, Redis in this case serves as a database in memory. This vote is then processed by the worker, which is an application written in .NET. The worker application takes the new vote and updates the persistent database, which is a Postgres SQL in our case. The Postgres SQL simply has a table with the number of votes for each category, cats and dogs. In this case, it increments the number of votes for cats, as our vote was for cats. Finally, the result of the vote is displayed in a web interface, which is another web application developed in Node.js. This resulting application reads the count of votes from the Postgres SQL database and displays it to the user. So that is the architecture and data flow of this simple voting application stack. As you can see, this sample application is built with a combination of different services, different development tools, and multiple different development platforms such as Python, Node.js, .NET, etc. This sample application will be used to showcase how easy it is to set up an entire application stack consisting of diverse components in Docker. Let us see how we can put together this application stack on a single Docker engine using Docker run commands. Let us assume that all images of applications are already built and are available on Docker repository. Let us start with the data layer. First, we run the docker run command to start an instance of Redis by running the docker run Redis command. We will add the -d parameter to run this container in the background, and we will also name the container Redis. Now, naming the containers is important. Why is that important? Hold that thought. We will come to that in a bit. Next, we will deploy the PostgreSQL database by running the docker run postgres command. This time too, we will add the -d option to run this in the background and name this container db for database. Next, we will start with the application services. We will deploy a front-end app for voting interface by running an instance of voting app image. Run the docker run command and name the instance vote. Since this is a web server, it has a web UI instance running on port 80. We will publish that port to 5000 on the host system so we can access it from a browser. Next, we will deploy the result web application that shows the results to the user. For this, we deploy a container using the result-app image and publish port 80 to port 5001 on the host. This way, we can access the web UI of the resulting app on a browser. Finally, we deploy the worker by running an instance of the worker image. Okay, now this is all good, and we can see that all the instances are running on the host. But there is some problem. It just does not seem to work. The problem is that we have successfully run all the different containers, but we haven't actually linked them together. As in, we haven't told the voting web application to use this particular Redis instance. There could be multiple Redis instances running. We haven't told the worker and the resulting app to use this particular PostgreSQL database that we ran. So how do we do that? That is where we use links. Link is a command line option which can be used to link two containers together. For example, the voting app web service is dependent on the Redis service. When the web server starts, as you can see in this piece of code on the web server, it looks for a Redis service running on host Redis. But the voting app container cannot resolve a host by the name Redis. To make the voting app aware of the Redis service, we add a link option while running the voting app container to link it to the Redis container, adding a -- link option to the docker run command and specifying the name of the Redis container, which in this case is Redis, followed by a colon and the name of the host that the voting app is looking for, which is also Redis in this case. Remember that this is why we named the container when we ran it the first time, so we could use its name while creating a link. What this is in fact doing is it creates an entry into the etc host file on the voting app container, adding an entry with the host named Redis with the internal IP of the Redis container. Similarly, we add a link for the result app to communicate with the database by adding a link option to refer the database by the name db. As you can see in this source code of the application, it makes an attempt to connect to a Postgres database on host db. Finally, the worker application requires access to both the Redis as well as the Postgres database. So we add two links to the worker application, one link to link the Redis and the other link to link Postgres database. Note that using links this way is deprecated and the support may be removed in future in Docker. This is because, as we will see in some time, advanced and newer concepts in Docker Swarm and networking supports better ways of achieving what we just did here with links. But I wanted to mention it anyway so you learn the concept from the very basics.
So we just saw how the voting application works on Docker. Let's now see how to deploy it on Kubernetes. So it's important to have a clear idea of what we are trying to achieve and plan accordingly before we get started. So we already know how the application works, and it's a good idea to write down what we plan to do. So our goal is to deploy these containers, these applications as containers on a Kubernetes cluster and then enable connectivity between the containers so that the applications can access each other and the databases, and then enable external access for the external facing applications, which are the voting and the result app, so that the users can access the web browser, right? So how do we go about this? Now, we know that we cannot deploy containers directly on Kubernetes. We learned that the smallest object that we can create on a Kubernetes cluster is a pod. So we must first deploy these applications as a pod on our Kubernetes cluster. Or we could deploy them as replica sets or deployments, as we have seen throughout this course. But first, for the sake of simplicity, we will stick to pods in this lecture, right? And later we will see how to easily convert that to a deployment. So once the pods are deployed, the next step is to enable connectivity between the services. So it's important to know what the connectivity requirements are. So we must be very clear about what application requires access to what services. We know that the Redis database is accessed by the voting app and the worker app. The voting app saves the vote to the Redis database, and the worker app reads the vote from the Redis database. We know that the PostgreSQL database is accessed by the worker app to update it with the total count of votes, and it's also accessed by the result app to read the total count of votes to be displayed in the resulting web page in the browser. So we know that the voting app is accessed by the external users, the voters, and the result app is also accessed by the external users to view the results. So most of the components are being accessed by another component, except for the worker app. Note that the worker app is not being accessed by anyone. You can see arrows going into all of these components, but there are no arrows going into worker, which means none of the other components or external users are accessing the worker app. The worker app simply reads the count of votes from the Redis database and then updates the total count of votes on the PostgreSQL database. So none of the other components nor the external users ever access the worker app. Now, while the voting app has a Python web server that listens on port 80, and the result app also has a Node.js based server that listens on port 80, and the Redis database has a service that listens on port 6379, and the PostgreSQL database has a service that listens on port 5432. The worker app has no service because it's just a worker and it's not accessed by any other service or external users. So keep that in mind. So how do you make one component accessible by another? Say, for example, how do you make the Redis database accessible by the voting app? Should the voting app use the IP address of the Redis pod, perhaps? No, because that can change. The IP of the pod can change if the pod restarts. And you may also run into issues when you try to scale your applications in the future. The right way to do it is to use a service. Now, we learned that a service can be used to expose an application to other applications or users for external access. So we will create a service for the Redis pod so that it can be accessed by the voting app and the worker app. And we will call it a Redis service, and it will be accessible anywhere within the cluster by the name of the service, Redis. So why is that name important? The source code within the voting app and the worker app are hard-coded to point to a Redis database running on a host by the name Redis. So it's important to name your service as Redis so that these applications can connect to the Redis database. And this is not a best practice to hard-code stuff like this within the source code of an application. Instead, you should be using environment variables or something. But for the sake of simplicity, we will just follow this application as it is developed, right? Now, these services are not to be accessed outside the cluster, so they should just be of type cluster IP. So we will follow the the same approach of creating a service for the PostgreSQL pod so that the PostgreSQL DB can be accessed by the worker and the result app. So what should we name the PostgreSQL service? If you look at the source code of the result app and the worker app, you will see that they are looking for a database at the address DB. So the service that we create for PostgreSQL should be named DB. Also note that while connecting to the database, the worker and the result apps pass in a username and password to connect to the database, both of which are set to Postgres. So when we deploy the Postgres DB pod, we must make sure that we set these credentials for it as the initial set of credentials while creating the database. Now, the next task is to enable external access. So for this, we saw that we could use a service with a type set to node port. So we create services for voting app and the result app and set their type to node port. Now we could decide on what port we are going to make them available on, and it would be a high port with a port number greater than 30,000. So we'll do that when we create the service. So we're done and we have the high-level steps ready. So to summarize, we will be deploying 5 pods in total, and we have 4 services. One for Redis, another for Postgres, both of which are internal services, so they are of type cluster IP, and we then have external facing services for voting app and the result app. However, we have no service for the worker pod, and this is because it is not running any service that must be accessed by another application or external users. So it is just a worker process that reads from one database and updates another. So it's not going to require a service. Now, I say that again as that's a common question that I get when we talk about services. Why does this worker not require a service, right? So a service is only required if the application has some kind of process or database service or web service that needs to be exposed, that needs to be accessed by others. In this case, that's not true for the worker app. Now, before we get started with the deployment, note that we will be using the following Docker images for these applications. So these images are built from a fork of the original developed at the Docker samples repository. The image names are codecloud/example voting app _vote with a tag of v1, and then again worker v1 result v1. And for the databases, we will use the official Redis and PostgreSQL releases that are available. Right, so that's it for now, and we will see this in action in the upcoming demo. In this demo, we're going to deploy the voting application on our Minikube cluster. So here I have created a new project folder called voting app. So the first thing that we are going to do is to create the pod definition files for each component within the application. So let's begin with the voting app itself. So we will name this pod definition file as voting app pod.yaml. And let us build this pod from scratch. So we will begin with the API version and set it to v1, and the kind will be pod. The metadata section would have the name which will be voting app-pod. And let's add a couple of labels. The first label would be the name, which can be the same as the name of the pod, which is voting app-pod. And the second label will be the name of the application, which is the demo voting app. So we will kind of use that label for all the components part of this application stack. That way we can group the components of a single application together by assigning the same kind of label to all of them. But there would still be a different label for each component to differentiate from each other. So let's add the spec section, and here the first thing that we're going to add is the name of the container. So we'll use voting app as the name of the container, and the image, we will make use of the custom image that we have built from the Docker samples voting app Git repository page, which is here. So we will use the custom images that we built under the Code Cloud Docker Hub repository.
The name of the image here is codecloud / example voting app _ vote with a tag of v1. Now we will also specify the port for this voting application as a container port property. So this should be the port on which the application listens for this voting app, and we know that it's port 80, so we'll set it to port 80. Next, let's create the pod definition file for the result app. So again, I'm going to create a new file here called a result app pod, and because this is a pod definition file like before, we can simply copy the template from the voting app file we just created, and then we will just make changes to the name and labels and the image. So let us change the name to result app pod, and we will make the same change to the label, and then the app label will remain the same, as all of these are part of the same app. And again, let's make the change to the container name to result app, and here the image will also be changed to codecloud / example voting app _ result, and with the same tag of v1. And the result application is also exposed on the container port 80, so we will leave that as is. Next, let's create the pod definition file for the Redis pod. So I'm going to name the pod definition file as redis-pod.yaml. And again, I'm going to make use of the previous pod as the template, and we will change the name of the pod. So we'll change it to Redis pod, and we will use the same as the label. And let's name the container as Redis, and the image should also be Redis. And the container port for Redis, we will change it from port 80 to 6379 because this is the default port for the Redis image. So let's save this. And now let's create another pod. Now this time for our database, we'll name it postgres-pod.yaml. And as before, we're going to copy paste one of the pod definition files here, and we'll make changes to the name. So this one will be postgres-pod, and the same for the label. Now the name of the container would be Postgres, and the image, we can also use the Postgres image itself without any tag, which means that it will make use of the latest Postgres image. The container port for PostgreSQL database is 5432 by default, so we will add that in. And we also have to add a couple of other environment variables here. So this is to make sure that we specify the Postgres username and password for the database. So as we saw in the previous lecture, the source code of the worker and the result pod has the password for the PostgreSQL database hard-coded in them. So we must specify the initial password to be set for the database here as environment variables. Now, a better way to do this would be to use secrets or some kind of vault to pass in these credentials and not have these credentials in a plain text format in a file, but those are out of scope for this course. We discuss about these concepts in much detail in our advanced courses on Kubernetes, the CKA and CKAD courses. We discuss about environment variables, services, secrets, and other concepts. So for this example to work, we have to make sure that we specify these two environment variables in the Postgres pod definition file. So for this, we will make use of an env section, which is a list of dictionaries, and we will have the environment variable name and value entered in them. So it must be Postgres_user for the username and Postgres_password in as a password, all in caps. Now the value for both would just be Postgres for now. And again, just to reiterate, we are adding these values because the worker pod and the result pod uses these credentials while connecting to the database. And if you don't configure these, the worker will not be able to connect to the database. And as a result, the total voting count may not
add up, right? So in case you run into issues with the vote count not updating or not able to view the results, then this is probably an area that you can check. So now we've created 4 pods: the Postgres pod, the Redis pod, the 2 front-end application pods, the result app and the voting app. The last one is the worker pod. So let's create a new file for the worker pod, workerpod.yaml, and I'm going to copy and paste the definition file. So in here, let's make changes to the name. So let's change the name to worker pod, and the same for labels. And the name of the container will be worker app, and the image is worker instead of vote. And one important change here is that we must remove the ports section, because as we discussed, the worker app has no services listening, so no port definition is required. So as a result, we can delete this entire section over here. So we now have 5 pod definition files for all our microservices. Next, we will create services to expose these pods, except for the worker. So let's get that going. Let's start by creating the service definition files. So let's start with one of the internal services, which is Redis. So we'll call the file as redis-service.yaml. So we will start with the API version, which is v1, and the kind is service. Let's add the metadata, and the name of the service we will use as Redis itself. So remember that this is important, and we'll add a couple of labels. The name would be set to Redis-service, and the second one is the one we have been using for all the other objects, which is demo voting app. Now next we will add the spec section, and within this we will add the ports. So for Redis, we know that the port to be used is 6379, and we'll also add the target port, which is also going to be 6379. Now we don't need to specify anything else like a node port, because this is going to be an internal service. Now let us add the selector. So in order to link the service to the pod, we must specify the same labels configured for the pod. So let's copy the labels from the pod definition file, and we'll paste it under the selector section. Now, since this is an internal service, we're not going to expose it outside on the network, so that should be good. So this file is now complete. So let's save it, and next we will proceed with the creation of the Postgres service. So now let us create the Postgres service file. We'll follow the same approach as before. We'll name this as Postgres service.yaml, and the easiest way to create a service now is to just copy the contents of the Redis service file and paste it here. So again, we will make the appropriate change. So if you remember the architecture from the lecture, the name of the Postgres database must be DB. So this is because the worker app expects the name of the Postgres database to be DB. So if you name it anything else, you'll find that the connection will fail. So we'll now change the labels. These labels could really be anything, so it doesn't really matter. Let's name it as Postgres service, and we can even name it as DB service. And let's change the port to 5432, because that's the port in which the Postgres database runs. And again, this will be 5432. And let's make sure that we copy the labels from the pod definition file. So here we will copy the name label, which is set to Postgres pod. So let's delete the older selectors and the labels, and then replace it with the new one. So now we're done with the 2 internal services. Let's now proceed to creating the external facing services, which is the voting service and the results service. So let's start with the voting app service. Let's create a new file called votingappservice.yaml, and we will copy the contents of the other file and then paste it here. Again, let's change the name to voting service. Let's change the label as well. And we know that this is a front-end application which runs on port 80. So let's set that port number as the service port and as the target port. And as before, we'll copy the labels from the pod definition file. So the next step would be to create the final service, which is the result service. So let's call the file as the result app-service.yaml, and let's copy the voting app service definition file into here. And then again, we change the name to result, and everything else is the same. And we will update the selector section with the labels of the pod, the result app pod. We actually created them as internal services like the others. Now, we have created the voting app and result app service as internal services like the others, but they are supposed to be externally accessible. So we must set their type to node port. So since we have not specified any type, it would be considered as cluster IP. So let's do that now. And each service requires, we'll set the type to node port, and each service also requires an additional port specification for the node port, and we will set that to 30,004 for the voting app. Okay, now we will go and update the same on the result service. So we will set the type to node port, and we will add a node port port number of 30,005 for the result app service. Okay, so we are done with all the files. We have completed the creation of all the pod and service YAML definition files, and we will now proceed with the creation of these objects, and we will then try to access the application on the web browser. So we will switch to the terminal of our system, and we are in the voting app directory, which is where we created all the pod and service definition files. So now we can start creating these objects. So first, let's check if there are any pod or deployments or services running on the server. So when we see that there's nothing except for the default Kubernetes service. There's nothing else running. So let's start with the pod and the service for the voting application, right? So we'll start with one by one, and we'll test and make sure that they're working as expected, and then we'll proceed further. So to create the pod, we will use the kubectl create command and specify the pod definition file. And similarly, let's create the service using the service definition file for voting app. So let us now inspect the status of the pod and the service. So if we want to see the pod and the service in a single command, we can run the kubectl get pods command and specify the service as svc separated by a comma. And so it will list both the objects. So we can see that the service for the voting app is created, and it is of type node port, and the pod is also created, and it is in a running state. Now before we proceed further, let's test to see if that bit is working, right? So what we could do is simply access the voting app service using a URL which could be formed by the IP of the Minikube node. So if you know the IP, you could just use the port number, which is 30,004, the port number of the service, and view it in a browser. Or if you're not sure about the IP, you could run the command minikube service and specify the name of the service with the --URL option. Okay, and it'll give you the URL that you can use. So we'll copy the URL, and we will try to access this in our local browser on my system. So here I'm at the local browser, and I'm going to try and access this, and as you can see, we are now able to load the voting application. So that's one step which is complete. Now let's not try and cast any vote for now, as we don't have the databases ready. Now let's go ahead and create the remaining objects, the pods and services. So back to the terminal, the next pod and service that we created is the Redis pod. So we run the kubectl create command with the Redis pod definition file and then the service file. And as before, we run the kubectl get pods and service command. And as you can see, the Redis pod and service are created. The service is now the cluster IP because this is an internal service. And let's create the Postgres database now. We'll create the Postgres database with the Postgres pod definition file, and as well as the service definition file for creating the service. Again, let's check the status, and we can see that the Postgres pod is in a running state, and similar to the Redis service, we can see also that the Postgres service is up as well with its name set to DB. Right, so now that both our Redis and Postgres pods and services are up and running, we can now create the worker pod. And to do this, we will use the kubectl create command with the worker pod definition file. So let's check the status of the pod, and I can see that the worker pod is also now in a running state. Now finally, let us create the pod and service for our result application. So let's do the same thing as before. Run the kubectl create result app command, and let us run the create the result app service as well. Okay, so now let's check the status of all the pods and services, and now you can see that all of our 5 pods are up and running. And we can see that we have 2 node port services, one for our result service and one for our voting service. The other 2 services that we created are the Redis and database service, which are internal only. So we've already accessed the voting application. Let us also generate the URL for our result service. So for that, I'm going to use the same command as before, the minikube service voting service command will give us the URL to access our voting app, and let us change the name here to get the URL of the result app. Okay, so we now have both the URLs. So let's go back to our web page, and here we have the voting application, which is running on port 30004. Let's copy and paste the new URL. So this is going to be 30,005. So let's try and cast a vote here. So I'm going to click on the docs as selection. And here you can see that there's a check mark against the vote that we selected, which indicates that our vote has been recorded, as in it has been saved in the Redis database. And you can also see that below that there's this particular web page is being processed by the voting app pod. Now if we go to the results page, you can see that the docs application has 100% of votes, because in this case we just have 1 vote, and that was for dogs. And I can also change the vote if I want. So I could go back and click on cats, and I can see that the result has changed to cats. So that's our demo. We have successfully deployed a multi-tier application on a Kubernetes cluster, and we have confirmed that it's working, right? So the data actually goes through from one end all the way through the Redis database, through the worker pod, to the PostgreSQL database, and up to the result pod. So it's working as expected. Well, that's it for now, and I will see you in the next one. Okay, so this is what we saw in the last demo. So we deployed pods and services to keep it really simple, and we were able to access our application from a browser. But deploying applications as just pods has its own challenges. Deploying pods doesn't help us scale our application easily if we wanted to add more instances of a particular service. And if you wanted to update the application, like an image that was used in the application, then your application will have to be taken down while the new pod is created. So that may result in a downtime. So the right approach is to use deployments to deploy an application. So Let us now improvise our setup using deployments. So we choose deployments over replica sets, as deployments automatically create replica sets as required, and it can help us perform rolling updates and rollbacks and maintain a record of revisions and record the cause of change, as we have seen in the previous demos. So deployments are the way to go. So we'll add more pods if required for the front-end applications like voting app and result app by creating a deployment and setting the replicas to 3. We'll initially start off with just 1 replicas for each of these components, and later we'll see how easy it is to scale them to 3 or more, right? So we will also encapsulate the databases and the worker applications within deployments. So let's take a look at that now. So here I am in the Visual Studio Code, and this is the project directory which has all the pods and service definition files. So let's create a new file for the deployments. So we'll start with the voting app itself. So I'll name this file as voting app-deploy.yaml, and I'm going to use the split screen function so that I can open the pod and the deployment definition file side by side. So let's create the deployment file for the building the application by using the pod definition file as the template. So let's start with the API version, and it will be apps/v1. The kind will be deployment, and let's add the metadata. The name of the deployment would be voting app-deploy, and we'll add some labels. Next, let's add the spec section. So it has already pre-populated a couple of entries for us. So we should be specifying the number of replicas. And for all our pods, we're just going to stick to 1 replica to begin with. And since we are on a single node cluster, to save some resources. And under the selector section, I'm going to add the labels from the pod. So we use the match labels option, and then we will copy and paste the labels over from the pod definition file. Now under the template section, I'm just going to copy everything from the metadata to the end of the file and then paste it under the template section. Once done, we fix the formatting. Alright, so that looks good. So let's proceed with the next deployment, which will be the Redis deployment. So again, I open the Redis pod definition file, and just like before, we create a new file called redis-deploy.yaml, and then we will copy the contents of the voting app deployment file just to get started. And we will change the name of the deployment to Redis deploy, and the same for labels as well. So we'll stick to replica 1, and we will copy the labels from the pod definition file for Redis, and then we copy over the template from the pods and then paste it and then fix the formatting. So that's done, and we will proceed with the PostgreSQL deployment. Let's copy the Redis deployment file, and I'll open the Postgres pod definition file for reference, and let's make the changes to the names and labels and update the selector labels with the ones on the pod. And then move over the definition under the template section, and then we fix the formatting. Okay, so that looks all right. Next, let's proceed with the worker. So we're going to close this. Let's create a worker app deployment file, and we will copy and paste the template and update the name. And let's copy the labels from the pod definition file and put it under the selector section. And the same as before, let's copy the pod manifest file and paste it under the template section. So that's the deployment for worker. And now we're left with one for the result app. So again, we close these two, and here is our result app. We will create a new file, result app deploy.yaml, and we copy and paste a template again, and we update the name and labels and the template as we did before. So we are now done with all our deployment definition files, and I'm going to get rid of all of this. So here is all the new deployment files that we created. And now let's head back to our terminal and create these deployments along with the services. So before we do that, let's make sure that there are no pods and services running in the cluster. So we have cleaned up everything that was created for the previous demonstration. So there are no pods or services other than the default Kubernetes one. And now let's refresh and make sure that all our deployment files have been created. So here we have the 5 new deployments that we created, and the services will remain the same. So we'll first start with the voting app deployment. So we'll create it using the kubectl create command and pass in the voting app deployment file as input. And let's also create the service, and let's do a quick check on the deployment and make sure that it's running. So yes, we see that it is in a running state. So now let's create the Redis deployment, and followed by the Redis service. And similarly, let's create the Postgres deployment and the Postgres service, and let's make sure that everything is up. So we see that all the pods are up. The deployments are running 1 out of 1 pods, which means that the pods are up and running. And let's check the service. So we have the DB service, we have the Redis service, and the voting app service created so far. So now let's clear the screen and we create the worker deployment. Now remember, the worker does not have a service, so let's make sure that everything is running as expected. And we see that the worker pod of the deployment is running as well. So finally, we create the result app deployment and the result app service. And we now see that everything is running as expected. So let's change this to deployments, SVC. So we have all the 5 deployments in a running state, and we have 4 services. So now let's get the URLs for our 2 front-end services. So we'll use minikube service and the name of the service with the URL flag. And let's do the same for the result service as well. And we get the URLs with the ports 30,004 and 30,005. So now I'm going to launch the web browser, and we'll try to access these applications. So let's look at the first URL, which is the voting app itself, and let's get the vote. And let me open another window here, which will go to 30,005. And you can see that the result is shown as expected. So now I'm going to scale up the deployment. So run the kubectl scale command and specify the number of replicas to 3 to add 2 more replicas for the voting application. So when we run the get deployments command, we see that there are 3 pods for the voting app right now. Now, if we now go to the URL and refresh the page each time, we see that the page is served by a new pod each time. So we see how easy it is to scale our applications with deployments. Well, that's it for this demo. I will see you in the next. We are at the end of the Kubernetes for Beginners course. I hope I have covered enough topics to get you started with Kubernetes. We started with containers and Docker, and we looked what container orchestration is. We looked at various options available to set up Kubernetes. We went through some of the concepts such as pods, replica sets, deployments, and services in Kubernetes. We also looked at networking at a very basic level in Kubernetes. We also spent some time on working with kube control commands and Kubernetes definition files. I hope you got enough hands-on experience in developing Kubernetes definition files. And finally, we also saw how to deploy a sample microservices application on Kubernetes on Google Cloud Platform. It was really nice having you for this course. I hope you gained enough knowledge and experience to get started with Kubernetes at your work or otherwise, and I wish you good luck in your Kubernetes journey. See you in the next course. Until then, goodbye. In this lecture, we will look at the kubeadmin tool, which can be used to bootstrap a Kubernetes cluster. The kubeadmin tool helps us set up a multi-node cluster following the Kubernetes best practices. As we discussed, the Kubernetes cluster consists of various components such as the kube API server, etcd, controllers, etc. And we've seen some of the requirements around security and certificates to enable communication between these components. Installing all of these various components individually on different nodes and modifying the configuration files to make sure these components point to each other and setting up certificates to make it work is a tedious task. The kubeadmin tool helps us by taking care of all of those tasks. Let's go through the steps to set up a Kubernetes cluster using the kubeadmin tool at a high level. First, you must have multiple systems or virtual machines provisioned for configuring a cluster. We will see how to set up your laptop to do just that. That's if you're not familiar with it. Once the systems are created, designate one node as master and others as worker nodes. The next step is to install a container runtime on the hosts. We will be using Docker, so we must install Docker on all the nodes. The next step is to install kubeadmin tool on all the nodes. The kubeadmin tool helps us bootstrap the Kubernetes solution by installing and configuring all the required components in the right nodes in the right order. The next step is to initialize the master server. During this process, all the required components are installed and configured on the master server. Once the master is initialized and before joining the worker nodes to the master, you must ensure that the network prerequisites are met. A normal network connectivity between the systems is not sufficient for this. Kubernetes requires a special networking solution between the master and worker nodes, which is called as the pod network. The last step is to join the worker nodes to the master node. We're then all set to launch our application in the Kubernetes environment. We will now see a demo of setting up Kubernetes using the kubeadmin tool in our local environment.
In this demo, we will see how to provision VMs for our Kubernetes cluster that will include a single master node and 2 worker nodes. And we're going to accomplish this by using 2 different pieces of software. The first one is going to be VirtualBox. So this is our hypervisor, which is ultimately responsible for running our virtual machines. And the other tool is going to be Vagrant. So this is like a automation tool that makes it really easy to spin up a whole bunch of VMs with a specific configuration. So we're going to make use of Vagrant so that all of us can kind of follow along with the exact same configuration for our VMs, and we can get those VMs up and running with just one single command. So the prerequisites, obviously, for this video is you have to install VirtualBox and you have to install Vagrant. So if you take a look at VirtualBox, you could just go to the virtualbox.org, and there's going to be a downloads page, and you could just select the specific operating system you're using, and then you could just follow the steps. Pretty simple. And then Vagrant, if you go to the Vagrant documentation, they have a walkthrough on how to install Vagrant as well. A couple of different ways to do that depending on what your operating system is. Just use whichever is most convenient for you. Now, for Vagrant, we have a Vagrant file, which is going to contain all of our configurations for our VMs. And this file has already been written out for all of you guys, and you can find that at the repository for the course. So go ahead and just clone this repository so that you can have access to the Vagrant file, and you can use that to spin up the VMs. And to clone the repository, all we have to do is go to this code dropdown right here and just copy the URL of this specific repository. Then once you do that, go to your terminal and run a git clone and then pass in the URL. And that's going to clone the repository. All right, so I cleared out the terminal, but after we clone the repository, it's going to create a folder with all of those files. And so I'm going to cd into that folder. And within here, if I just do an ls, you should see the Vagrant file right here. So let's open up the Vagrant file and let's take a look at the configuration. All right, and so in the configuration, you can see here we've set it up to have one master node and two worker nodes. The IP addresses for the host, so this has nothing to do with Kubernetes yet, the IP addresses of the actual VMs or the nodes, they're going to make use of the 192.168.56 network. And if you'd like to, you can go ahead and poke around at the rest of the configuration, but we don't need to worry too much about that. The great part about Vagrant is we could just run one command and get all of our VMs up with the same exact configuration. So I'm going to close this out. And I'm going to run a Vagrant status. And so what this is going to do is it's going to check the status of the VMs. And for these statuses for the VMs, we can see that they're all set to not created. And so you could see that we've got the three different VMs here, KubeMaster, which is going to be our master node, and then the two worker nodes. And they're all in a not created state because we actually haven't brought up the VMs. So let's go ahead and do that now, and we can do that with the Vagrant up. And this is going to provision all three of those VMs with the exact specifications from the Vagrant file. And so what it's going to do is it's actually going to pull the Ubuntu Bionic 64 base image. And then once that image is pulled, it's able to then provision all of the different VMs. This part is going to take a decent amount of time to get all of those VMs up and running. So we're just going to have to sit there and wait. Just understand that it's not a big deal if it takes a long time. It's kind of expected. Okay, so now that it's complete, if you just take a look at the logs, you can see it actually goes step by step and provision the different VMs. So it first started provisioning the KubeMaster. After it provisioned that, it then moved down to the Kube node 1, which is the first worker node. And then it wrapped up by provisioning the Kube node 02. So we've got all three VMs provisioned. And now if I do a Vagrant status, we can take a look at the status of the VMs now that they're provisioned. And we can see that all three nodes are in a running state, which is exactly what we want. So now that we've got the three nodes in a running state, how do we connect to it? Well, we do this by running the command vagrant SSH, and then the name of the specific node we want to connect to. So if I want to connect to KubeMaster, I'm just going to copy that. And this is automatically going to connect us to the KubeMaster node. And so now you can see based off of the command prompt, you can see we are now in the KubeMaster. And if I just do an ls-la, we could see that I am in fact in the KubeMaster. So to log out, to exit out of the session, I can just do a log out. And that's going to take me back to my local machine. And if I once again do a Vagrant status, I can then do a Vagrant SSH and I'll connect to Kube node 1. And connected to Kube node 1, if I just run an uptime, we can see that it's been up for 3 minutes. So we are in fact connected to Kube node 1. And then I'll log out of this one and then we'll just quickly connect to Kube node 2. So I'll do a Vagrant SSH Kube node 2. And now we're successfully connected onto Kube node 2. So that's how you access all of your VMs. So we've got all of our VMs provisioned and we're good to go. So in the next video, we're going to actually bootstrap the Kubernetes cluster using kubeadm. Okay, so we have created all of the VMs that will act as our nodes necessary to get started with creating our Kubernetes cluster. So we've got 3 nodes. We've got 1 master and 2 workers. And so just to make sure you guys understand which tab is which on my screen, you have the KubeMaster here, and that's going to be this tab right here called KubeMaster. And then we have Kube node 1, and then we have Kube node 2, which is going to be the 2 worker nodes. Now, to get started installing a Kubernetes cluster, what we're going to do is we're going to reference the documentation. And you specifically want to go to this installing kubeadm page. So this is going to walk you through the process of getting everything set up with kubeadm. And it's going to have all of the necessary links that you can refer to get all the other aspects of a cluster up and running. So this is the main page you want to start at. Just remember that. I think it's always good to remember which part of the documentation is where you want to look. And so let's quickly just go over the prerequisites. And so that's going to be under the before you begin section. So it's going to say you need to have some sort of compatible Linux host, whichever distributions are supported, and which we have successfully done in the last lecture. We deployed a couple of Ubuntu VMs, so those will meet the requirements. Here are the specs that it needs to match. So it needs to have 2 gigabytes or more of memory, and it also needs to have 2 CPUs or more. And then this is just going to go over some of the other requirements that are necessary for all of your nodes. So let's go down and let's go to this section right here where it says installing container runtime. So we're going to have to install a container runtime on all of our nodes. Which runtime you want to install is completely up to you. In this demo, we're going to install containerd. So just select this, and I'm going to actually open this up in a new tab. And so this is going to, once again, refer to a different page within the Kubernetes document, specifically the container runtimes page here. And this is just going to walk you through all of the steps necessary to get a runtime up and running. And regardless of which runtime you're using, the first thing that you're going to have to do is follow the instructions right here where it says forwarding IPv4 and letting IP tables see bridge traffic. So this is just pretty easy. All you have to do is just copy this, and we are going to run this on all of our nodes. So that's going to be both the master and the worker nodes. So I'm going to go to the master, and I'm just going to paste it here. And you should see an output similar to this. And I'll paste it here as well. And we'll do the last worker node. And after you do that, there's going to be a couple of commands that you can run to verify that everything's running. Here, we're going to verify that the BR, NetFilter, and overlay modules are successfully loaded and running. And we're going to want to do this on all 3 of the nodes. So I'll start in the master. Okay, so we see both of them are running there. And we have verified that it's running on all 3 nodes. The next thing that you want to do is verify that the following system variables are set to a 1. So we can just copy this line right here. Run it, and we can see that all of the system variables are set to 1, 1, and 1. Okay, so everything is good to go. So let's now go to the runtime that we're interested in, and we'll just select containerd. So it's just going to move us down the page, and it's going to tell us the instructions that we will need to follow. So let's click on this getting started with containerd. I'm going to open this up on another page. It's going to take us to a GitHub page. And there's a couple of different options of installing containerd. You could use the official binaries, but I'd rather just use, apt install. So here, option 2, to install it using apt, go ahead and select your distribution. We are using Ubuntu. And that's actually going to take us to the Docker page. And so the process for installing containerd is going to be very similar to installing Docker Engine. So we're just going to actually follow this page here. And I'm going to make this bigger for you guys. So let's go ahead and follow these steps. The first thing that we want to do is set up the repository. So we can just copy this and paste this once again on all 3 nodes. Okay, so we've done that. The next thing that we want to do is add the Docker official GPG keys. And we're going to run this once again, all 3 nodes. And then we'll set up the repository. And after the repository setup, let's go ahead and do a apt update. And once again, we're going to do this on all 3 nodes. And while that's running, let's take a look at the final step. And the final step is to run this command where you install all of the different packages. But remember, we're not interested in installing Docker or anything Docker related. We just want containerd. So we don't actually have to copy this entire command. All we need is sudo apt install, and then we just need containerd.io. So just copy that name. And now we can run this on here. So we'll do sudo apt install, and then we want containerd.io. And I'll copy this command, and we'll run this on both of the other nodes. And after that's installed, we can do a systemctl status containerd, and we can see that it's actively running. So the installation was successful. Now, before we move on to the next step, there's actually one more thing we have to do with containerd. And if we actually scroll up on this page, and so I'm still on the container runtime page, we want to go to this C group driver section. And this section is kind of important, and I definitely recommend you guys kind of read through it just to kind of digest and understand it. But just to kind of give you a brief overview of what this section is saying, there's this thing on Linux machines called control groups. And these control groups are used to constrain resources that are allocated to different processes running on your machine. Now, both kubelet as well as the container runtime actually need to interface with these control groups to enforce various resource managements for pods. So think of things like setting the CPU and memory requests and limits. These are all things that need to be kind of communicated to the C groups. And so the kubelet and the container runtime kind of have to interact and interface with these C groups. And so to interface with these control groups, kubelet and container runtimes need to use a C group driver. And there's two different drivers. There's C group FS, and there's systemd. So C group FS is usually the default. Systemd is the other one. Now, which one you use is going to depend on a couple of different things, but the rule is if you are using a systemd init system, you have to use the systemd C group driver. So that means we're going to have to change it because I did mention the C group FS is the default for the container runtime. And in addition to that, whatever driver is being used by the kubelet or the container runtime, the other one has to be used as well. So if the container runtime uses systemd driver, C group driver, then your kubelet has to use the same exact systemd driver. You can't have one using C group FS and one using systemd. They have to both match. So we're going to set both of them to be systemd. So let's go ahead and do it for the container runtime. And first of all, let's verify what our init system is. And if you don't know how to do that, there's a very simple command. If you just run ps, so this is going to list out all the processes, and you grab the one with the process ID of 1, that's going to be your init system. And it's going to give you which init system. So this one's systemd. So we are in fact using systemd. And so to set the C group driver to systemd, if we go down to the containerd section, we're right down to here, we got containerd. Configuring the systemd C group driver, you have to go to the /etc containerd config.toml, and then you have to configure this. So we're going to copy this for now. And we're going to do a sudo vi /etc containerd config.toml. And this is important. Go ahead and delete all of the default configurations. You might run into some errors if you don't. Go ahead and just delete all of it. So I'm going to delete all of that. And then we're going to paste in the configuration. And I'm going to delete this line right here where it's just the 3 dots. And that's all you have to do. So we will save that. And then we'll do a sudo systemctl restart containerd. So the changes take effect. And we're going to do that for all 3 nodes. So I'll do sudo vi /etc containerd. I'm going to delete everything, and then we'll paste the config in, and then delete that line. And then we'll restart containerd. And we'll do it for the last worker node as well. All right, so the runtime is ready to go. We've got that off the checklist. Let's go back to the documentation. We want to go back to the installing kube-adm page. So this is the original page we're on. So we've got the installing container runtime done. we'll go to the next section. So the next section, we're going to install kubeadm, kubelet, and kubectl, just to kind of reiterate what all of those do. So kubeadm is actually the tool that's responsible for bootstrapping the cluster. Kubelet, that's going to be the component that runs on all of your clusters that's going to do things like starting your pods and containers. And then kubectl, that's the command line utility that we use to talk to the cluster. So let's go down here. And so this is going to contain the section that has all the instructions for installing kubeadm. And this is just going to be a cut and paste job. So I'm just going to copy this first step. And we're going to run this. And make sure to run this on all 3 nodes. We'll copy step 2. We're going to add the repository now. Okay, so we've added the repository, and then we can get all of those installed. All right, so now we've got kubectl, kubeadm, and the kubelet installed on all 3 nodes. Okay, so now we can get started on configuring or provisioning our Kubernetes cluster. So we'll go to the what's next section down here. It's going to take us to this create a cluster page, which is just going to link to the same page. So we'll go there. And this is going to go over all of the steps. Once again, you see the prerequisites. Here, you just need to make sure you have Ubuntu or CentOS or one of the distributions that's supported. And then here's all the other specs that we saw on the other page. And we want to go down to this page, this section right here where it says initializing your control plane node. The first step right here, so this command, this control plane endpoint, this is only if you're going to run with multiple master nodes. We just have one, so we can skip the first step. But for the second step, we have to choose, first of all, you have to choose a pod network add-on. And then on top of that, when we run the kubeadm init command, which is what's actually going to create our cluster, we have to pass in this --pod-network-CIDR flag to provide what is going to be the pod network that we're going to use. So in our case, we're going to use the 10.244.0.0/16. So we'll have to pass that in. The third step right here, this is basically is telling us that kubeadm will try to automatically detect which container runtime we're using. If it can't do that, you can pass in the -scri socket flag and pass in the what is the specific path to your specific container runtime. But kubeadm will automatically detect that we're using container D, so we don't need to worry about that. And the last thing is when we run the kubeadm init command, we're going to also have to pass in the --API server -advertise -address flag. So this is going to basically specify what is the address that the API server is going to listen on, and we're going to set it to be the correct static IP that we set on the master node, which will ultimately make the API server accessible to all of the worker nodes on that specific IP address. So here we just pass in the IP address of our specific master node that we set. All right, and so now all we have to do is just run kubeadm init, and then we pass in those 2 flags. Remember, we want the --pod network flag and the --API server advertise address flag. Now, before we do that, I'm actually going to go back to the previous page. And if we go back to this cgroup driver thing that we talked about, where we have to set it to be, either systemd or cgroupfs, I did mention that the kubelet also has to be set to systemd. Now, the great part is, starting in version 1.22, the cgroup driver defaults to be systemd. So that's exactly what we want, so we don't have to do anything different. However, if you're using a version before that, you're going to have to create a kubeadm config file, and you're going to have to specify this configuration right here. So kubelet configuration, and then specify the cgroup driver as systemd. And then when you run the kubeadm init command, you pass in the --config flag, and then pass in that YAML file that you configured. So we don't have to do that because we're using systemd, but I just wanted to make sure we pointed that out. So now let's go back, and we're going to run the kubeadm init command with the 2 flags that we want. And we're going to do this just on the master node. Okay, so don't do this on all 3 nodes, just the master node. So we'll do kube ADM init, right? And then the first one is going to be the --pod-network-CIDR. And I'm going to set this to be 10.244.0.0/16. And then we want to specify the address of our API server. So we'll do --API server -advertise-address equals. And what's the IP address? Well, hold on. I actually have to go check that real quick. So I'm just going to comment this command out so it doesn't actually run. And we'll do an IP add. And so take a look at this interface right here. This is going to be the 192.168.56.2. So this is going to be the IP address of our API server. So let's go ahead and run that same command. And I'll set it to 192.168.56.2. And I'll delete the comment. And we'll let that run. And that's not kube admin, it's just kube ADM. And you have to make sure that you do this with root privilege, so do a sudo. Okay, so after our control plane has successfully initialized, there's going to be a couple of things that we got to do. And make sure you don't delete what's on your screen. You actually need these steps. So the first thing is a admin.conf file was actually created so that we can actually connect to our Kubernetes cluster. So what we're going to do is we're going to create a .cube folder in our home directory. And it's going to copy this admin.conf file into that directory so we can connect to our Kubernetes cluster. And then we're going to also change some permissions so we can use it. So just take these 3 commands and just run this just on your master node. And so now you should be able to connect to your cluster. So if I do kubectl get pod, right? So we see no resources found in the default namespace. So that means we've successfully connected to our cluster, but it's just, we have no pods deployed. So that's perfect. Then the next step is saying is that we have to now deploy our pod network. And so you can see all of the different network add-ons that we can use to actually set that up. So that's going to be what we're going to do next. We're going to set up the pod network. And then after that, we'll have to then go to our worker nodes and then run this command. So this is going to join the worker nodes onto our Kubernetes cluster. So definitely copy this command and make sure it doesn't get deleted because we're going to need that later. All right, so let's click on this link. It's going to take us to the add-ons page. So here we've got the different networking add-ons that we can use. In this demo, we're going to use WeaveNet. So I'm going to select the last one down here, which is WeaveNet. And so for installing WeaveNet on a cluster, all you have to do is just run this command right here. So kubectl apply, and this is going to deploy a daemon set that's going to run on our 3 nodes. So I'm going to copy this, and we're just going to run this command. So I'm going to run this just on my master node. All right, and it's going to deploy a daemon set as well as a couple of other things. So if I do a kubectl get pods -A, so we can see all of the pods across all namespaces, we should see that we have 1 pod that's getting deployed on our control plane node. And that's what we expect. We deployed a daemon set. We're not going to see it on the worker nodes because we haven't had the worker nodes join the cluster yet. So you're only going to see just 1 instance of the WeaveNet pod. Now, before we move on from this section, if you actually take a look at the documentation, it's always good to read all of the documentation because there are always gotchas when we're working with all of these different technologies. Down here, under the things to watch out for page, just kind of hidden, if I zoom in for you guys, it says, if you do set the cluster CIDR flag option on kubeproxy, make sure it matches the IP alloc range given to WeaveNet. So this is just basically saying that when we ran this command up here and we specified the pod, we're going to make sure that this same network is passed in using the IP alloc range environment variable. So if I actually go down, there's going to be an example down here where it's just under the container, the Weave container, we have to specify an environment variable and then pass in the specific network that we're using. So we just have to make sure they match. So we're actually going to edit and modify the specific deployment. So if I do kubectl get daemon set, and we're going to do -a to get all of the, we're going to take a look at the weavenet. So I'll do a kubectl edit daemon set weavenet, and then -n cube-system. And we want to look for the container. And so we can see the container here, that this is the weave container. So let's add in another environment variable. And what was it again? We'll just copy this. And we'll set the value. And this is going to be the 10.244.0.0/16. Okay, so that's all we have to do. And make sure you set it on the right container. So we want specifically the one that's the weave container. There's a couple other containers in this daemon set. So just make sure you get the right one. And we can then exit out of this. And that's going to edit the daemon set. And if we just run kubectl get pods-a, we should see it's terminating the old one, and it's going to create a new one. So we'll give that a couple minutes to get deployed. All right, let's do a kubectl get pods-a again. And we can see we've got the new weave pod deployed 16 seconds ago. So we're good to go. So we have set up the networking. Now the last thing that we got to do is we got to join the worker nodes to the cluster. So let's go up, back up to where that command was, this kubeadm command, and we want to just run this on our 2 worker nodes. So I'm going to copy this. We're going to run this on worker node 2, and don't forget to run this with admin privileges with sudo. And after it's completed, you should get a message saying this node has joined the cluster. So go back to the master node. We'll do a kubectl get nodes. And we can see we've got the 2 nodes. This one's still in a not ready state. So let's just run this again. And we can see now it's in a ready state. So we've now successfully joined the worker nodes to the cluster. Let's verify that everything's working. And we're going to do this by running a kubectl, and we'll just deploy some random container. So I'll say kubectl run, we'll just deploy an nginx container. So I'll say --image equals nginx. So we've got the pod created. We'll give that a second to start up, and then we'll just do a kubectl get pod. And we can see that it is, in fact, in a running state. And we'll just go ahead and delete it now. Do a kubectl get pod now. It's deleted. So we have successfully bootstrapped our own Kubernetes cluster from scratch using the kubeadm tool. And that's going to wrap up this demo. Thank you for watching.
Hello and welcome to this lecture on setting up Kubernetes. In this lecture, we will look at the various options available in building a Kubernetes cluster. So there are a lot of ways to set up a Kubernetes. We can set it up ourselves locally on our laptops or virtual machines using solutions like Minikube or Micro K8s. These are solutions for developers or those who want to just play around and learn Kubernetes. The kubeadmin tool is used to bootstrap and manage production-grade Kubernetes clusters. There are also hosted solutions available for setting up Kubernetes in a cloud environment such as GCP, AWS, Azure, or IBM Cloud, and many others. We also have a demo on provisioning a Kubernetes cluster on GCP. And of course, these are just a few among the many options available to deploy a Kubernetes cluster. So you may really follow any of these approaches to set up a Kubernetes cluster, but to go through this course, you don't really need to set one up. As part of this course, we give you a real Kubernetes cluster that you can access right in your browser
with the click of a button without having to set anything up. And we have guided challenges and fun hands-on lab exercises that will get you familiar with Kubernetes in no time. In this section of the course, we will just start with one of these options. The remaining examples are in the appendix section at the end of this course. So we will start with the Minikube option, which is the easiest way to get started with Kubernetes on a local system. If Minikube is not of interest to you, and you just want to rely on the online labs, then now would be a good time to skip this lecture. So before we head into the demo, it's good to understand how it works. Earlier, we talked about the different components of Kubernetes that make up a master and worker node, such as the API server, the etcd key value store, controllers, and scheduler on the master, and the kubelets and container runtime on the worker nodes. It will take a lot of time and effort to set up and install all of these various components on different systems individually by ourselves. Minikube bundles all of these different components into a single image, providing us a pre-configured single node Kubernetes cluster so we can get started in a matter of minutes. The whole bundle is packaged into an ISO image and is available online for download. Now, you don't have to do that yourself. Minikube provides an executable command line utility that will automatically download the ISO and deploy it in a virtualization platform such as Oracle VirtualBox or VMware Fusion. So you must have a hypervisor installed on your system. For Windows, you could use VirtualBox or Hyper-V, and for Linux, you could use VirtualBox or KVM. And finally, to interact with the Kubernetes cluster, you must have the kubectl Kubernetes command line tool also installed on your machine. So you need three things to get this working. You must have a hypervisor installed, the kubectl utility installed, and Minikube executable installed on your system.